All right, now we're on to our last unit. So for this half, we're going to talk about capacitors and their uses in circuits. So to begin, we're just going to define capacitors. So what is a capacitor? Well, we just define capacitors as two separated conductors holding equal and opposite charges. So usually this just involves taking two metal shapes and separating them somehow. And what is this idea of capacitance? Well, we define capacitance as the amount of charge you're able to store per unit of potential difference. So you can almost think about it as how efficiently your device stores charge, because as charge builds up, you create a potential difference, and that is sort of your limiting factor. For example, you could be limited by a battery. So if you can store more charge per volt, you have a better capacitor. And it turns out this is entirely geometric. So the only way to affect capacitance is doing something to the geometry. So you could increase length, you could increase separation, you could put a dielectric material in the space. So you can't actually improve your efficiency by putting more charge, for example. So let's set these up. So there's only three types of capacitors we need to be able to deal with in Physics C, although most of them are going to be the parallel plate. So first we have our spherical capacitor, where we just have two spheres, and you're given their individual radii. So you might be given their two radii, where your big radius is R2 and your little radius is R1. So first of all, you just have to remember from Gauss's law what expression applies. And due to the fact that the charges are equal and opposite, there's only ever going to be a field in the between the metals region. So here it's going to look like a sphere slash a point charge. And we know what that field is. That is going to be our electric field. Is just 1 over 4 pi epsilon naught, or K, if you will, times Q divided by R squared. So to find the potential difference, we have to use an integral, because again, to get capacitance, it's charge per volt. So you need to evaluate that delta V integral. So our potential difference is going to be the negative integral from R1 to R2 of our E field, which is 1 over 4 pi epsilon naught times Q over R squared dr. This evaluates nicely because the Q and the 4 pi epsilon naught are constants. So we're just left with the integral of 1 over R squared dr. And that ends up working out to Q over 4 pi epsilon naught times 1 over R2 minus 1 over R1. And yes, I know that will be a negative quantity. That's totally fine because we know our capacitance expression is just going to be Q over delta V. And in this case, our Q is just Q. And our delta V in absolute value would be Q over 4 pi epsilon naught times 1 over R1, because I want the big number second, because I want this term to end up being positive. So again, the sign doesn't matter when dealing with capacitance, because we're just taking this positive quantity. We want the absolute value of the potential difference. And this works, right? Because if R1 is a big number, we want R1 to go first in this expression, because if you divide by a small number, you get a large result, whereas here, you can think about plugging in a really big number, so you're subtracting something less. So we can simplify this and show that it is only based on geometry. And we get this expression. And the only things that affect it are the sphere radii and epsilon, which we assumed was epsilon naught, but we could change that by putting a dielectric in here, for example. All right, next we got a cylindrical capacitor. So this could actually look the same as the previous one if you're given like a cross-section view, but really what we have is just two cylinders. And we have the same idea where we're given actually their length as well. And we're also given the individual radii of each of our cylinders here. So, of course, we can see which one this is similar to. This Gauss's law base case would be our line of charge. So we will use a cylinder / line. And this is in our known results list, and we've probably derived it a lot. But we get that E from a line is not actually inverse square, but it's actually just inverse. So when we do our potential difference, we'll get a slightly different result. So we still integrate in the middle region as per usual. We can pull out everything that's not the r. So we get 1 over negative lambda over 2 pi epsilon naught. And then we integrate from r1 to r2 of dr over r. And since it's not r squared, but r to the 1 on the bottom, we get a special integral. So this would be negative lambda over 2 pi epsilon naught times the natural log of r2 divided by r1. And of course, we'll just flip the sign later. So once again, our potential difference is defined as the charge divided by the potential difference in absolute value. Now the charge on this cylinder is not lambda, right? Lambda is the charge per length. So if lambda is Q divided by L, Q would be lambda times L. So Q is lambda L, and delta V is just the absolute value of our expression from earlier. So we see the 2 pi epsilon naught comes up to the top, and we're left with the natural log of the radius ratio. So we can see, once again, we're just left with geometry factors. So the length of the cylinder matters, which makes sense, right? Because you should be able to pack more charge on the cylinder if it's longer before you get the same potential difference. And then it makes sense the radii are also involved, because that's dictating your sort of space you have to work with. All right, what about parallel plate? This is actually the easiest one. It involves the least calculus. So this is just our classic parallel plates. They're separated by a distance d. Now from Gauss's law, we actually know that this is going to be most similar to a plane / an area charge. And our formula we have from Gauss's law is that E from a plane is equal to sigma over 2 epsilon naught. But in this case, a parallel plate system between the plates is actually due to 2 plates. So we actually get E total is equal to sigma over epsilon naught because it's 2 plates. So we do have to be careful of that field involves a doubling, because there's not just 1 plate, there's actually 2. So you have to be careful of that. Alrighty. Now our delta V starts off kind of the same, where we just integrate from 0 to d of just the E field, sigma over epsilon naught times dr. But there's actually no dependence here on the distance, right? That's one of our weird features of the plate, is that there's no dependence on distance at all. So we can actually just use our old friend for a constant field. Delta V is actually just equal to ED. So in this case, it's just our E field sigma over epsilon naught times our distance d. All right. Now we can do the same thing once more. Q over delta V. Wow, can't talk. Q over delta V is our capacitance. What is the Q? Well, I'm given the area charge density, sigma. So if I did everything in terms of sigma, which is charge per area, Q would be sigma times area. And then potential difference, we said, was sigma d over epsilon naught. So we get epsilon naught A over d, which is very close to our parallel plate formula. And I say very close because it's missing a kappa in case we add a dielectric. So these are the cases you should be able to derive. Again, derive, not memorize. Like there's no expectation you memorize this formula or this formula. You should know this one, although it is on the formula sheet, but you should be able to derive the others. So what happens if we add a dielectric? Well, a dielectric, by definition, polarizes in the E field, which is going to lower the E field strength. Because what eventually happens is if we imagine drawing a little dielectric here, we have a capacitor, we insert this dielectric material, and what happens is that you have these molecules in here where, let's say that my original electric field might point something like this. Well, what that's going to do to the molecules inside the dielectric is the positives would like to go with the electric field, the negatives would like to go against it. So we actually get something which we have been calling the back electric field, where you get a small E field that opposes the stronger E field from the plates. So what happens is that the net E field is going to decrease because these molecules are fighting the applied E field. Now, what does that actually do? Well, if we're just going to assume an isolated capacitor for this, although we can figure out how to make it work with a non-isolated one. So if you have an isolated capacitor, which is kind of the setup to this problem, meaning the charge can't change, well, you essentially have the same distance, but a weaker E field. So that is going to decrease the potential difference. So we define this kappa as the factor by which the net field is decreased by the addition of the dielectric. So essentially what we have is that delta V is equal to ED, and our E field has been divided by kappa, and our distance stays the same. So as a result, our potential difference was also going to decrease by a factor of kappa. Now, if we connect the capacitor to a battery, however, that forces this delta V to be fixed, which means the battery is going to dump more charge on the plates in order to counter this effect to keep the same E field as before. So why does the dielectric actually increase capacitance? Well, our formula for capacitance is capacitance equals the charge you can store per unit of potential difference. So all that means is that we said that the capacitance, well, the potential difference decreases by a factor of 1 over kappa. So that means that capacitance would increase by a factor of kappa because we're storing the same charge. So imagine you have a fixed charge on your capacitor. Well, a fixed charge would have a lower potential difference due to the weaker E field. So you're increasing capacitance by a factor of kappa. So what is the effect? Well, when you add a dielectric, the dielectric increases capacitance by a factor of kappa. So this means that C plates would just be kappa times the capacitance in a vacuum. So we get kappa times epsilon naught A over D. So anytime you have a dielectric, that is the most direct change. To figure out what's happening with the field and the potential, you have to understand if the capacitor is isolated or not. But absolutely, no matter what, the capacitance increases by a factor of kappa when you add a dielectric. All right, given a capacitance meter and a ruler, describe an experiment that can be conducted in order to calculate the dielectric constant of a material, include all the usual stuff. So if we want the dielectric constant of something, we probably need to put it in a capacitor, especially given the fact we're given a capacitance meter. So we want to place the material between two metal plates. We want to measure the plate separation and record capacitance for various values of D. So it involves having a material that can be placed between two metal plates like this so that we're allowed to use our plates formula. Then we take our capacitance meter, which works just like a voltmeter where you connect it one probe each between the two nodes that you want the capacitance between. And we have a formula that says capacitance is equal to kappa epsilon naught A over D. So this means that we can graph capacitance on our y-axis. And since we have a ruler, we're measuring plate separation for distance d. So d is our variable. So I might actually want to write that as kappa epsilon naught A times the quantity 1 over d. So I can get all of my variable kind of in one term here. So this means I can write it as kappa epsilon naught A times the quantity 1 over d. So we graph C versus 1 over d. And our slope is kappa epsilon naught A, which we can, of course, use to solve for kappa. Now, many of you are maybe slope purists, so you would like to shove epsilon naught A into the box as well, so kappa is just the slope. That's totally fine. Just might be a fun task figuring out what exactly the units on the y or on the x-axis are, because you have this lovely individual in your equation, so you have to look up what the units of that are. All right, now let's talk about energy. So what's the energy stored by a capacitor? So by definition, the energy stored by a capacitor is 1/2 Q delta V. And that might seem odd because I thought energy was Q delta V. Well, it's 1/2 Q delta V because you don't have to push all of the Q across a delta V to charge the capacitor. Right, as the capacitor charges, it becomes initially not difficult at all to move charge, but then it becomes more difficult, more difficult, more difficult. So what you end up getting actually, it's the other way. I want to graph it the other way. So if you graph the potential difference as a function of Q, you would get sort of this straight line. And the area under this curve sort of gives you the energy. And we see it's a triangle shape, so it's 1/2 Q delta V. Because it doesn't actually cost you the entire delta V potential difference every time you move a bundle of charge. It's only this final bundle of charge that would cost delta V. So it makes sense it's somewhere between 0, because it costs 0 to push the first bundle, and it costs Q delta V to push the last bundle, so it's got to be somewhere in the middle. And since capacitance is a linear quantity, it actually is exactly half the average there. So now we can find two different versions. So this is usually not helpful because it's rare that you would know how things change with both Q and delta V. Usually you'll know capacitance. So we want to get C involved in each of these. So first of all, let's say we know, let's say there is a known charge. So this would be if your capacitor is isolated on a little island. So if there's a known charge, that means we can use the fact that we'd say U is equal to 1/2 Q delta V, which is equal to 1/2 Q. And since we know that the definition of capacitance tells us C is equal to Q over delta V, we can replace delta V with Q over C to get 1/2 Q squared over C. So if charge is fixed, if you know the charge only, usually it's helpful to look at this one. And if we have a known voltage, we'll do a similar substitution, except if we solve for Q, we can find that Q is equal to C delta V. So we get 1/2 C delta V squared. So this is helpful if we have like a battery that's enforcing a potential difference. And when I say useful, I mean in terms of determining factors of change without having to figure out both Q and delta V. Usually you'll know how one of them changes or stays the same. So on that topic, an isolated capacitor by definition, is a capacitor that is not connected to anything. So the charge on the plates cannot change because it's just living on an island. There's nowhere for the charge to go. So this means since Q can't change, C and delta V must change to maintain constant Q, because Q equals CV. And then conversely, connecting to a battery enforces potential difference, so you can change C and Q to maintain a constant delta V. So here's our original values, and we're just going to do a couple of changes and solve for all this stuff. So we have a battery that remains connected. Capacitor remains connected to a battery of potential difference delta V. So instantly, we see remains connected to a battery. So this means absolutely, no matter what else happens, we know we have a fixed delta V. So the potential difference is absolutely a delta V. All right. The plate separation is then doubled by an external force. So plate separation, well, that's not any of these. That's actually geometry. So what is plate separation going to affect? Well, that's capacitance, right? Capacitance is kappa, we'll use black, is kappa epsilon naught A over D. So what is plate separation? Well, plate separation is D. So I'm doubling the plate separation, which means I have half the capacitance. All right, now let's pick a bunch of stuff to do. Charge on positive plate. Well, what do we know? How can we get charge? Well, these three variables are related. So I can use the fact that Q equals C delta V. Delta V, by definition, remains fixed, and the capacitance halved. So my charge must also have halved. And it makes sense because delta V is Q over C. So Q and C must be doing the same thing in order to get that same delta V. All right, what about electric field? Now, there's a couple ways of doing this. I think the easiest is looking at the equation delta V equals ED. So what do we know? Well, we know the plate separation doubled, but we also know that the delta V remains constant. So what must happen? Well, if D doubled and V stays the same, the E must have been halved. So we actually get a weaker E field. That makes sense because it corresponds to this charge halving. There's another way you could have actually done it, where you could have said the E field is sigma over epsilon naught, and said that which is charge per area, that the charge halved and the area stayed the same, so sigma got halved. That's an alternate way. Now, what about the energy stored? Pick your favorite. Just to avoid the squaring, maybe let's just use the definition. 1/2 Q delta V. Don't get tricked by that 1/2. That 1/2 is just a multiplier. We're only looking at the ratios. So delta V remained fixed, but the Q got halved. So that actually means our energy stored also got halved. So there's our values there. Now we'll do the same thing, except the charged capacitor remains isolated. And we put a dielectric inside. So what does that do? Well, the most direct thing it does is capacitance increases by a factor of kappa. So if I insert a dielectric with kappa equals 3, capacitance triples. So that is the most direct change. But we are given that this capacitor remains isolated. So the most direct constant tells us that Q is fixed. So I know I have constant charge, but I have triple the capacitance. So what does that mean? Well, our potential difference, we said, could be found using the relationship Q over C. So we're tripling the capacitance, which means our voltage drop is going to be cut by a factor of 3. And this should make sense, because if I'm packing the same amount of charge on a larger capacitance, it shouldn't drop as much voltage, because we've gotten more efficient at storing charge. Now I'll do the same thing. Delta V is equal to ED. D stayed the same. Delta V got multiplied by a third, so that means electric field must have also gotten multiplied by a third. That also makes sense because we have an isolated capacitor. And if our capacitor is isolated, we can just use this relationship. So I caution against using this all the time. This only works for isolated capacitors. For an isolated capacitor, you can totally just divide the original E field strength by the dielectric constant. Now, energy stored, we know everything, so let's just use 1/2 Q delta V. Delta V was divided by 3, and Q remained constant, so this is an energy decrease. Now, it's easier to conceptualize this energy decrease because if you insert the dielectric, that causes the molecules to polarize. So it costs energy for the molecules to polarize, which is why you're not storing as much energy. So that's basically any capacitor multiplier you could be asked. All right, all that just to get done with one section. All right, capacitor networks. What happens when we connect capacitors in series? Why does capacitance decrease? Well, in series, we're increasing the effective plate separation, which decreases capacitance because D is on the denominator for plates. So C series is actually the opposite of how resistors work, where we get the reciprocal rule. So then to build symmetry, we know that the parallel rule must just be straight up addition. So again, it is important to realize that series and parallel rules flip for capacitors. It also makes sense why the factors do their individual contributions, because if we look at the capacitance formula for plates, we see that parallel, you're effectively increasing area, so C goes up, but for series, you're effectively increasing distance, so C goes down. Now, remember for resistors, everybody in series is part of the same loop, so they get the same current. And in parallel, every resistor had the same voltage drop because if we colored our circuit, we see they got the same color change, or more fundamentally, Kirchhoff's loop rule, right? If they make a loop with each other or a loop with the battery, you have to drop the same volts. So parallel is the same. It's still just potential difference. But capacitors, we don't really talk about the actual current. We usually are just looking at steady state. So we look at not the rate at which charge is flowing, but just the charge itself. So series, it's the same Q. Parallel, it's the same delta V. And here's a tricky one. When capacitors are connected to each other, it could look series or it could look parallel. But the answer is actually definitively parallel because you're just connecting two metals to each other. And if you connect two metals to each other, you know they're equipotential surfaces. So you're just guaranteed it's the same potential difference between the plates. So that is parallel. So even though it looks series, like I can totally draw, like if I draw something like this, this definitely looks like it's series. And it would be series if there was a battery here. But this is actually parallel because the capacitors form a closed loop with each other. So here's the representative example. So consider the two capacitors below, which become connected by closing a switch. We want to derive expressions showing each of the following facts. At equilibrium, conductors are equipotentials, and the total charge remains constant because there's no other objects here. All right, so connected conductors being equipotentials, that just means delta V across each of these capacitors must be the same. So we can write that as Q over C equals Q over C. We don't know Q1 and Q2. This just tells us the total. But we can't actually figure out their ratio from this because our first capacitance was 2 microfarad, where our second capacitance was 8 microfarad. So this actually tells me that multiplying both sides by 8, this actually tells me that Q2 is equal to 4 times Q1. Which makes sense, because if we have the same potential difference, but this capacitor has 4 times the capacitance, then I must have to put 4 times the amount of charge on that capacitor's plates to get the same potential difference, because it is 4 times as efficient. All right, total charge remains constant. This one's easier. This just says Q1 plus Q2 must be equal to Q total, which is a constant. And what do we look at here? Well, positive plate has 10. Well, top plate has 10. Top plate has 20. Does actually matter signs here. Q1 plus Q2 would be equal to 30 microcoulombs. There can be canceling if you connect the positive plate of one to the negative of the other. That is actually possible. Not necessarily common, though. All right, calculate each of the following: equilibrium charge on each capacitor, voltage across each capacitor, energy stored. All right, let's do it. So we have two equations now. Our first equation we derived said Q2 equals 4Q1. Our second equation said Q1 plus Q2 equals 30. So let's substitute for Q2 in the second equation. So we can get Q1 plus 4Q1 is equal to 30. So 5Q1 is equal to 30. So Q1 is equal to 6 microcoulombs. All right, my 8 microcoulomb. Well, we just said that Q2 is equal to 4 times Q1. So it's equal to 4 times 6 microcoulombs, which is equal to 24. So Q2 is 24 microcoulombs. All right, what's the voltage across the 2 microfarad capacitor? Well, delta V is defined as Q divided by C. Our Q1 was 6 microcoulombs, and our C1 is 2 microfarads, so that gives us 3 volts. Now, for the 8 microfarad capacitor, if we did the problem right, it should match. Now we have 24 microcoulombs for the 8 microfarads, so it makes sense that this works out because we quadrupled the charge in order to compensate for the quadrupled capacitance. Now let's find the total energy stored. So we can add the energy stored by each individual capacitor. Then we can use the total charge of the system and equivalent capacitance. So I think it's easier just to probably use 1/2 Q delta V. We'd use 1/2 Q1 delta V1 plus 1/2 Q2 delta V2, which is equal to 1/2. Q1 is, I already forgot, 6. Delta V1, and I'm going to do this in microjoules. Delta V1 was 3, and then we have 1/2 times 24 times 3. That's equal to 936. All right, 12 times 3 is 36. 3 times 3 is 9. Makes sense to me. So we get 45 microjoules. Now we can quickly check that this makes sense because we can actually use equivalent capacitance because we said these are actually parallel. So CEQ is actually the 2 capacitances in parallel. So these 2 capacitors, 2 and 8, make 10 because they're in parallel. Capacitance adds in parallel. And we can just use U equals 1/2 C delta V squared, which is equal to 1/2 times the capacitance, which is 10, times delta V, which is 3. So we get half of 10, which is 5, and 3 squared is 9. So I can give a sigh of relief because it works out. So you can actually simplify this problem. You don't have to do all these steps in the linear system. You actually don't have to do that if you recognize these are just 2 capacitors in parallel. You can get their voltage sort of for free just by dividing the total Q, you can actually check that delta V at equilibrium is just Q tot over CEQ. And in this problem, there was 30 microcoulombs to go around, and the total capacitance was 10 microfarads, which is equal to 3 volts. So you can actually see that it works out by just combining the capacitors. All right, now we have a symbol circuit example. Rank the charge on each of these plates. So we'll actually draw it out. So we have a combination circuit here, just with capacitors. And I already can't draw. So notice these aren't in series and they aren't in parallel. We have this sort of combination. So we have to use 3 colors. So we have 3 distinct potentials. And we first want to rank the charge. So notice that we have this sort of junction rule idea here, where some of the charge is going to split between the 2 and the 3. So we know for sure that Q on the capacitance C is larger than the others. I don't want to put them in order yet. Now, let's think about how the charge splits. So notice they actually have the same delta V, the 2C and the 3C. And if the 3C has a larger capacitance, that means you can pack on more charge before you get the same potential difference. So that means the 3C capacitance must actually win the split over the 2C because you need more charge to get that same yellow to blue potential difference. And we can see my justification here. The capacitance C is before the junction, so you get all the charge there. Then the charge splits, and the 2C gets less because you don't need as much charge here to get that same potential difference. Now let's rank potential difference. So what we know for sure is that delta V across the 2C is equal to delta V across the 3C. Now we just got to decide how the original capacitor compares. And I actually made this more straightforward for the potential difference than the combination circuit example of this with resistors, where if you look at this, we see that the C capacitance has more charge across it, right? It gets all the charge, but also it has lower capacitance. So Q is bigger, C is smaller. So delta V is certainly bigger across the C capacitance. So we know the 2C and 3C must have the same potential difference because of the parallel rule, and the capacitance C holds more charge and lower capacitance. So we don't even have to do any ratios. We see that we have a larger Q but a smaller C. Those two effects both cause delta V to increase. All right, we gotta solve it. Gotta solve it now. So usually we gotta break this down into a single capacitor. So first thing I'll do is I'll find CEQ. And my equivalent capacitance, we can see I can combine the 2C and 3C into parallel. And then I have a 1C in series with that. So my equivalent capacitance is going to be 1 over C plus 1 over 2 plus 3 is 5 to the negative 1. All right, fraction arithmetic time. So we know it's going to be a multiple of C. So I know it's C times whatever 1 plus 1/5 to the negative 1 is. So we get C times 6/5 to the negative 1, or 5/6 times C. That is helpful for us, because now that unlocks the total charge in the network. And it makes sense that we get a value less than C because one of our inputs into the series formula is C. So if you're ever doing the reciprocal rule, your answer needs to be smaller than all your inputs. So this actually told us that for the whole network, our equivalent capacitance is 5/6 C. our delta V is epsilon, because that's the battery EMF. And then what is Q? Well, Q is defined as C delta V from the capacitance definition. So the total charge supplied by the battery is 5/6 C delta V. So the total energy stored is just going to be 1/2 Q delta V. So I can multiply these two numbers and then divide by 2. So I would get 5/12 C times script E squared. All right, why does that help? Well, now we can start marking up our diagram again. So what we know is that this capacitor has a charge of the entire battery charge, right? It's just going to be 5/6 C epsilon. And why that's helpful to us is because we now have two of the 3 capacitor quantities. So we have Q, we have C, we want delta V. So we can say that delta V is Q over C, so we just take out the C, and we get actually 5/6 script E across that. So that actually tells us that we know for sure that you get the entire battery charge, right? Just like if it was a resistor, it would get all the battery current. All the charge is on the first one, because there's no splitting that happens. So delta V, we said, is Q over C. So we just take out a C from that. And then energy. For our energy, we do the same thing. We're just going to do 1/2 Q delta V. So 1/2 Q and delta V. Oh, this is lovely looking. 25 over 36 divided by 2. 25 over 72? Wow, that's ridiculous. That was an awful choice. That was an awful choice for me. I imagine that's correct. Now for the 2C, now we have to do Kirchhoff loop rule. Because now we know the voltage drop across this portion is 5/6 of the battery EMF. So the remaining 1/6 must be across either capacitor in our loop. So we know for free, just because we found the voltage drop across the first part of the loop, we know we get 1/6 here. So now we have to determine the splitting. So to determine the splitting of the charge, we can actually kind of reason through it, because this capacitor has 1.5 times the capacitance, so it should split in that sort of ratio, but we can just use the fact that Q is equal to CV to do this. So the fact that Q is CV means that we can just multiply each of their capacitances by this. So the 2C, that gets a 1/3 C epsilon, because we get 2 over 6, and then we get a 3 over 6, which is 1/2. And notice, if we add 1/2 and 1/3, we get 3/6 and 2/6, which does make 5/6. So the total charge does work out. All right, more lovely multiplying here. This is just going to be 1/36 C epsilon squared. And then we get 1/24 from the other one. Again, you just multiply these two boxes and divide by 2 once again. All right, now to check that it works out, we should hope that all these 3 numbers add to 5/12. All these multipliers. Is that going to work? Oh, I think all these actually go into 72, right? Yeah, they do. 36 times 2, 24 times 3, yeah. So this number is actually 2 over 72. And this number is actually 3 over 72. So if we actually add all this up, 25 plus 2 is 27. We get 30 over 72c epsilon squared, which is 5 over 12. Because 6 goes into 35 times, 6 goes into 72 12 times. Wow. I would not have guessed that. So it does actually work out. Ugly, ugly, ugly. All right, we'll conclude with some RC circuits. So we have to remember the behavior. So we have these compound RC circuits. It's just really important to know that short time capacitors are uncharged, so there's no resistance for current. They're not trying to pump current the other way or anything. So at short times, we have a gap. No. Short time, short circuit. This is a wire. So I'm going to redraw this using a wire. So we have a resistance R. Then I'm not going to draw my capacitor branch yet, so I can shamelessly copy paste later. So we get this. We get this as our simplified circuit. And we just got to figure out what to add to it. So we get to, so I just am not drawing the capacitor. I'm either going to shade in a wire or shade in a hole. So first, for short times, we said it's a wire. So I'm going to just assume it is a closed switch. And we can try to color code our circuit here. And if we do that, we see that we get a short circuit because my blue has managed to make it all the way around. So what that tells me is that my REQ is actually just R, because I can neglect all of this because all the current is going through the capacitor branch. So my I total is just EMF over resistance. All right, now for the long time. So long time, capacitor's charged. So that means there must be no current, because if there was current, the capacitor would still be gaining or losing charge, which is not happening. So there's no current down the capacitor branch, which means we have a gap in the wire. So you literally draw a hole there. Now we can color code once more. And now we get a different effect because the blue cannot make it across the gap. So if we try to color, actually, I'm going to do a little different. If we try to color, no, I was right the first time. It's Roy G-Biv, not Rio G-Biv. So we get this for my equivalent circuit. So we actually see that REQ, it's got to go through everybody. So 1 plus 2 plus 3 is 6. So my I total is 1/6 EMF over R. So we see very different behaviors, right? The capacitor, your RC circuit has a lot of current at the start and then lower current at the end, because you're going to end up shorting things at the start. But towards the end, the current has to go through all the resistances. All right, now let's do our table. Short time. Well, 2R and 3R were shorted, so there's absolutely nothing happening for those. Then what about our regular resistance? Well, our regular resistance, 1R, had all the voltage drop. So it just had the Ohm's law current, epsilon over R, and power dissipated. Pick your favorite formula. I'm going to use delta V over R for current, and then power dissipated is I delta V. No 1/2 for resistors. All right, now for the capacitance. Well, for the capacitance, it was not charged. So there's no charge on it, which means there's no potential difference and there's no energy stored. All right, let's do long time. So long time, this is just a big old series circuit. And we said the equivalent resistance was 6R. So we just found the Ohm's law current was 1/6 epsilon over R through everybody. Oh, this is going to look a lot like the last example with those numbers, isn't it? So our voltage drop we can just get with delta V equals IR. So we get 1/6 of the battery voltage. Then we get 2/6 of the battery voltage, which is a third. Then we get 3/6 of the battery voltage, which is a half. Then the same idea for power dissipated. Multiply these two together. 6 and 6 makes 36. 3 and 6 makes 18. And then 6 and 2 makes 12. Then for our capacitor, we know that we have to actually mark up the circuit for this. So a common trap is thinking it's the full battery voltage. It's not, right? It's because full battery voltage is red to blue. This is not red to blue. So here we see that the drop across the first resistance, R, was 1/6. So if this is 1/6 of the battery voltage, this must be 5/6. Well, it's actually the inverse of the other one, our other capacitor. Right, and you also could have done it by noticing that orange to blue is the same thing as going through each of these resistors. So it's going to be 1/3 plus 1/2, which is 5/6. That works as well. So our voltage drop is not the full battery EMF, but actually just 5/6 of it. So then we can find the charge using C delta V. So C is just C. So we get 5/6 C delta V, C epsilon. What about the energy stored? Energy stored, pick your favorite. This time we do need a 1/2. Multiply these two together. Divide by 2. Oh, it's 72 again, isn't it? Oh, that makes sense, because it's a capacitance C, which receives 5/6 of the battery voltage drop. Huh. What a nice little coincidence. We'll say that's intentional. Another thing we could do is we could check the power dissipated's work out. A 36th plus 2 36ths plus 3 36ths. That does give 1/6. Yeah, that makes sense, because the resistance was 6. Yep, this should all work out nicely. All right, now to conclude, we're going to look at our transient RC circuit to our diff EQ. So for our charging capacitor, this essentially looks like this. Our loop differential equation, we just go through all our components, where we would say the sum of the voltage gains and drops must cancel around a closed loop. We gain voltage across the battery. We drop some voltage across the resistor. We drop some voltage across the capacitor, and then we're back. Voltage drop across a resistor is I times R. Voltage drop across a capacitor is Q over C. Not a differential equation yet. We have to remember that charge, that current is the rate at which charge flows. So we can just write this I as dq/dt. No need to solve. But if you wanted to solve this for dq/dt, no, let's not. Maybe just to clean it up a bit, I might put the R in front of the dq/dt just to make it clear what the terms are, but we'll keep it like that. Now, this is a moment where we say just remember what the solutions look like. So we know that the charge on our capacitor should be like ramping up. So we know it follows the following parent function, where it's going to look like Q is equal to Q max times 1 minus e to the negative t over tau. So for our circuit, the maximum charge it can store would be Q equals CV, so C times epsilon times 1 minus e to the negative t over tau, which for a RC circuit is RC. Now, what does this graph look like? Well, this graph is our exponential approach. So it is going to level out and approach a maximum value. Alrighty, lovely. Now we'll do our decaying case. So for the decay, that would be our discharging capacitor. So for our discharging capacitor, that would look something like this. Where here, I actually would still start with the same loop equation. And I would say for this class, always include a battery. This will make your signs actually work out. Even if there's not a battery, always include a battery EMF term. And this helps you get the sign right. Like, there's a formal way of doing this by understanding something with the sign of DQDT. But you will always get it right if you include a battery term, and as soon as you remember the battery's not there, you wipe it out. Oh, there's no battery in this circuit. Goodbye. So I can say negative delta V across the capacitor minus delta V across the resistor equals 0. Delta V across the capacitor is Q over C. Delta V across the resistor is IR. And we get a very similar equation to last time. So always include this sort of phantom battery term. It guarantees the sign will be correct. Because you want a decaying exponential. So if you end up getting dQdt equals positive stuff times Q, you know you messed up the sign. I always include this phantom battery to make it work out. There's other ways of doing it that don't involve that, but I like this method. All right, what's the solution to this? Well, this is just a straight up decaying exponential. We're going to say our maximum charge is C times the battery EMF, and time constant of an RC circuit is still RC. So those are our two parent functions here. So if we look at what this function looks like, this would just be a decaying exponential. So anytime you solve a circuit differential equation, it's going to be one of these parent graphs. It's either the exponential approach, which is the max value times 1 minus e to the negative t over time constant, or you have just straight up exponential decay, which is max value times e to the negative t over time constant without the minus, without the 1 minus. All right, home stretch. Now we're just going to do some time constant shenanigans. All right, what's the expression for a time constant of an RC circuit? Well, for an RC circuit, tau is just equal to RC, as long as we take the equivalent resistance. So what does this represent? Well, it really represents how long it takes for stuff to happen. If you're charging, it's the time required to get to 63% of your final value. But if you're discharging, it's the time required to decay by 63% of your original value. So that's why sometimes you see 63, sometimes you see 37. Basically, after one time constant, you're 63% done with the process. Overall, it's the time required for stuff to happen. So if you have a larger time constant, your charge time is larger. All right, we got our circuit shown below here. We want the time constant of the RC circuit first. Well, it's just RC, as long as we take the equivalent resistance and capacitance. These resistors are in parallel, so this is 1 over 3 plus 1 over 6 to the negative 1. And 3 plus 6 is, of course, 2. And then here, we're in series, but remember, capacitors are opposite resistors, so we actually get 1 over 6 plus 1 over 3 to the negative 1 once again, and this is 2C. So even though they're in opposite configurations, they're both reciprocal rule in this case, right? Because resistors in parallel add via the reciprocal rule, whereas capacitors in series add, right? That flipping of the rule. So we have 2R and 2C. So our time constant is 4 RCs. So drive an expression in terms of tau for the time required for the capacitor to reach 50% of its steady state voltage. Well, doesn't actually matter if it's charging or discharging here, but this will be charging. So we can assume that if it's charging, even though we didn't solve for delta V, we know it's proportional to Q. So it's going to follow that relationship. So we know delta V is going to follow this relationship. All right, what does it mean to reach 50% of your steady state voltage? Well, that means delta V is 50% of V max. So this means 0.5 would be equal to 1 minus e to the negative t over tau. So e to the negative t over tau would be equal to 0.5. Then we'll take the natural log of both sides. So you'd get negative t over tau is equal to ln of 0.5. So we'd get t is equal to negative tau times ln of 0.5. But just to make this look more like a positive value, remember that the log rule says that we could write this as t times ln of 0.5 to the negative 1 power, and raising 1/2 to the negative 1 means flip it over, so we get ln2. And remember that it takes one time constant to reach 63%. So if we actually work this out, this better be less than one time constant, and it is. This is roughly 0.6. Ooh, am I going to get natural log? No, I know it's about 0.6. My guess is about 0.63, but we'll see. This is about 0.6 tau. Anyway, it's less than 1. All right, last up, we're just going to do the linearization, because this is the only time where you can't just shove this stuff in a box. Because if you're linearizing something with an exponential relationship, it only works with the decay. The trick is you can't just put this in a box because there's too many unknowns in the box. So what you have to do is you have to ln first to separate the t in time constant. So if we have I is equal to I0 e to the negative t over tau, since the exponent is what's messing us up here for our procedure, we need to ln both sides to get everybody out of the box. So we can break the log by the log product rule. And now you can only cancel log and e if they touch. So now you can cancel that. So we could write this relationship as ln of I is equal to negative 1 over tau times t plus ln of I0. So this is now linear because ln of I can live in its own box. T can live in its own box. And we have some constants. So negative 1 over tau is the slope. I0 is the y-intercept. And we have our function that we're graphing, y, the function of x here. So this is linear. Just center that more. All right, how can we use this graph to solve for the time constant and initial current in the circuit? Well, we know that negative 1 over time constant is equal to the slope. So this means that tau would just be negative 1 over slope. Then we also just know that ln of I0 is the y-intercept. So the regular value of I0, we'd have to undo the log from both sides. So we just raise e to the power of the y-intercept, which looks kind of odd, but it is the answer. All right, that's capacitance. Now that just leaves inductance.